Okay, welcome to the last hottest of 2018. We're pretty happy with how the first year's gone, and we're going to continue next year. I think the next talk will be January 24th, but it will be posted on the hottest webpage once it's firmed up. And as usual, this talk's being recorded, and assuming the speaker agrees, we'll post it on the YouTube channel. And you should feel free to subscribe to that YouTube channel. There's a link on the hottest website that gets you there. As usual, if you want to ask a question, just unmute your microphone and interrupt the speaker. But otherwise, leave your microphones muted so we don't get any feedback. And it's also nice for the speaker if you turn your video on, just to make it more obvious that there's a real audience there. The talk will last 60 minutes, then we have 30 minutes afterwards for discussion. So there's no other special announcements today, so I'll just introduce Eric Finster from INRIA in Rennes. And his title is Towards Higher Universal Algebra in Type Theory. Go ahead, Eric.
Well, thanks very much to Dan and Chris for asking me to speak. I'm happy to be here. So what I want to talk about today is some work in progress towards addressing the problem of how to do higher algebra, higher universal algebra in type theory. That is, how to deal with coherent objects, coherent structures on types. So just to place us in the context, I think everyone kind of is aware of this. There we go. Just recalling sort of how Voevodsky laid out his vision of what univalent mathematics looked like. He introduced this notion of H level, and he said that, that H level 0 corresponded to sort of the mathematics of Cantor, the mathematics of sets and structured sets, the mathematics of the 20th century that we're all very much used to. And that in the middle of the 20th century, we started to step outside that world, and we started to work at H level 1 with the mathematics of, well, let's say, most effectively employed by the Grothendieck school, although of course categories were invented by Americans. And working at H level 1 corresponds to working with groupoids and structured groupoids. Now, of course, that's a little historically inaccurate because most, I think, category theorists would say that they work with categories and the groupoids are a special case, but this was an intuition that I think Vladimir fought hard to come to accept. And that he sort of predicted that higher mathematics, the mathematics we see emerging today related to higher category theory, higher versions of algebraic geometry and algebraic topology, was the study of structures on homotopy types. So this was the start of a sequence of progression towards this newer kind of mathematics. So this is a really nice vision and something that I've grown to be very fond of, but it leaves open one sort of very serious question. And of course it was Voevodsky who sort of pointed out that Martin-Löf type theory and the way it treats equality and identity made it a kind of ideal system in which to develop this kind of mathematics. But it leaves open the question of how do we describe structures on homotopy types if we, in the absence of some kind of strict equality, because most approaches in traditional mathematics exploit the fact that we have strict models, set theoretic models of homotopy types and ways of describing structures on homotopy types that exploit strict algebraic structure. So this is a problem which has been, which has kind of persisted for a while in type theory. But let me point out that some special cases of this problem are known, or have solutions that we know of. So for example, I think some of the things Voevodsky did sort of count as solutions when he introduced the notion of contractibility and a homotopically correct notion of equivalence. These kinds of things, these turn out to be coherent structures, and it's not at all obvious a priori that they can be defined inside a language which has these coherence issues in which they need to be treated delicately. There are also other examples. Mike's a nice example of how to define fully coherent idempotence in type theory is a good one. Egbert has this nice theory of equivalence relations, exploiting some clever ideas from topology. And this list is not at all meant to be exhaustive, just some examples that came to my mind where we have been able to treat infinitely coherent structures inside of type. But of course, some structures that we would really like to treat are very much lacking. So a long-standing sort of approach to this problem, or proposed approach to this problem, has been try to construct some notion of semi-simplicial type. Try to use this to internalize the theory of infinity one categories in the way that it's been developed, for example, by André Joyal and Jacob Lurie. And then try to reduce other problems of coherent structure to this particular case, or hope that simplicial objects are universal enough somehow to encode lots of different coherence problems. And they certainly do encode a lot. That's not really a debate. But yeah, I would say, sorry?
Your audio keeps cutting out, and I wonder if it's maybe a volume problem. I think it's when you speak a little softer, it cuts out. But I'm not sure. So just try speaking.
Well, I'll try to project. I wonder if I hope I'm not covering the microphone or something like that.
I don't know, but it's mostly fine. Then it just cuts out now and then. So just maybe try speaking a bit louder.
It's filtering it because it's thinking it's background noise. You got to speak a bit louder.
Okay, I'll try to project. I'll sit up straight. I'm sitting on the couch here, so that might be the problem. Okay, so I just want to point out that in mathematics, many examples of higher structures already exist. You have iterated loop spaces, EN spaces, exotic things like ring spectra. There are notions of homotopy coherent Lie algebras and things of this sort. And there's also, that's coming from topology, coming from category theory. We have infinity n categories, infinity double categories, all sorts of interesting things in higher category theory. And maybe it's possible to reduce all these to simplicial methods. I'm not at all, That totally could be possible, but one might ask if this is the most efficient way to describe these kinds of higher structures. And it sort of naturally occurs that you might want to have some sort of more direct description. Why can't we sort of do higher algebra inside of type theory in a more direct way? Can we? So I'm sort of posing the question: can we find a natural class of structures that we can describe directly? So in this talk, what I'm going to try to do is propose an adaptation of a particular approach to thinking about coherent structure, which is the approach introduced by Baez and Dolan. They start with a theory of operads. I'm going to sort of recast that in the language of what are called Cartesian polynomial monads. So this is a certain kind of structure that is fairly familiar to category theorists, I think, a particular kind of a class of monads that one finds on sets that turn out to encode many interesting kinds of structure. And so I'm going to sort of today try to walk through, propose a definition of what such a thing is in type theory. So typically these kinds of monads are treated on the category set, or generalizations, maybe in a locally Cartesian closed category or something like this. And so for people who know what this structure is, that's the structure I'm aiming for. That's the best description that I can think of. And I'm going to try to describe what is a Cartesian polynomial monad on type. And it turns out special cases of this definition are things that we like. The finitary case turns out to correspond to infinity one operads. The unary case will give a definition of infinity one category. And of course, a special case of that is also infinity groupoid. So a consequence of this definition are a definition of some objects that I think a lot of us have been interested in for some time. And there's also a corresponding definition of algebra over such a monad. I doubt I will have time to describe this today. I won't have time to describe this today, so I'll have to leave that for another time. But there is such a definition of an algebra presented in a similar style. And the special cases of this definition are well-known things in topology. For example, the coherently associative types, types with a coherent associative multiplication, what are called A infinity types. Types with a coherently commutative multiplication, E infinity types, are also algebras over a polynomial monad. And then it turns out that if you look at an infinity one category as a special case, then an algebra for an infinity one category viewed as one of these monads turns out to exactly be a diagram over that category. So a special case of the definition of algebra will be a diagram indexed by an infinity one category. And so a corollary of these definitions is a definition of simplicial types. Because, for example, delta The simplex category is a one category and therefore an example of this definition. And so an algebra over delta viewed in this way is a definition of simplicial type. Now, whether it's a correct definition is something that it will take some time to tease out, to play with and see if it yields the kinds of theorems we want. But a consequence of this, of the definitions I'll give today is a definition of simplicial type. So where are we in terms of formalization? So is this an idea that works on paper or is this an idea that works in practice? So the formalization of the definition of monad I'm going to give today is complete and is done in Agda, and you can find it on my GitHub site. So I think that's pretty good evidence that this technique is amenable to formalization and that it can be carried out inside of type. And so as a consequence, there is sitting there a definition of any of the objects which are special cases of this, for example, infinity operads, categories, and groupoids. The definition of algebra requires a construction that I haven't finished formalizing yet. So I would have liked to have had that done for today, but such is life. It's sketched out and there's a bunch of, some equations left to check. So the definition of simplicial type that I'm proposing is not completely formalized yet today. But I would say that the on-paper definition is quite clear, and it's sort of clear to me that at least a definition will be possible to extract from this technique. It just turns out that the construction that it relies on is somewhat long. There's a lot of boilerplate that needs to be put in place before it can be finished. So that's where it is with formalization. So the things that I'm going to say today, exist already, and you can go look at the code and check it out. Okay, so I think I'm going to get started here. Are there any questions so far? This is a natural place to. No? Okay. In that case, I'm going to sort of try and run through the definition and how it works. Okay, so first, and the approach I'm going to take, I'm going to sort of try to describe things in very much in a way that's coming from universal algebra. So I want to think about signatures and what it means to have relations on signatures and what it means for those signatures to be coherent. So to introduce that, let's start with the definition of a polynomial. Now this is something that's pretty well known, I think, to type theorists. It goes in the name container in the computer science community. It's a well sort of established notion. I'm going to pick a particular representation, which is perhaps not the most standard, but is perfectly valid. It consists of fixing a type I of sorts, and then fixing a family of operations indexed by their output type. And then for each operation, you pick a family of input parameters, and this extra parameter I will be the type of the input parameter. So this is a particular presentation. So the parameters are grouped according to, sorry, I say type. I'm going to try to say sort for the sorts of operations, because type is going to be way too overloaded if I do that. But sometimes I might slip. So correct me if I make a mistake. Anyway, so for a sort I, an element F in op I is an operation of output sort, return sort I. And if I have an operation and an element J, then an element P in the type of parameters of F of sort J is an input of that particular sort, okay? So this is just describing our polynomial is a collection of typed operation symbols in the sense of universal algebra. So a more traditional notation might be something like this, where I write an operation symbol together with its sort of type of parameters, and here I'm just listing the sort of each input parameter and then a return sort. Okay?
Was the type that you wrote before, is that the universe?
Sorry?
You wrote on the previous slide. That's the universe, right?
Type, I mean the type of types in type theory. So a type family. So op here is just a family over the type I. Yeah, exactly. That's why I'm going to try to say sort. These things are elements of that type, and it is the type of sorts of my signature. It's kind of an extra. I hope that's not too confusing. Such an operation, I'm going to sort of be developing a graphical language to describe this definition. So operations will be depicted like this, as corollas with input wires depicting their inputs and output wires depicting their return source. And so, right. But I do want to emphasize that here in this picture, it looks like the type of parameters has 3 elements, and so that it's kind of discrete, and sort of necessarily my pictures will be like that. But I'm not making that restriction at all on the polynomial. So you can have higher types in both the operations and the parameters. We can have a space of operations indexed by a sphere, and we can have an operation whose input type is, say, a torus or something else. So I'm specifically allowing for this to be a kind of higher signature, and I think that's something we want. And actually, we'll see there are examples of that, very interesting examples of this. So so I'm definitely not restricting to discrete types there. Okay.
Sorry, I'm just trying to slow you down because this went really fast, and I'm just trying to.
Sorry.
So are I, J, K, are these all operations or?
So yeah, I'll try to use the following naming convention. So I've fixed this type capital I, which is just a type. It's going to be the type of sorts of my signature. So right. IJK, little ijk will be sorts, so okay. Elements of a particular type. Okay. The parameters I'll try to stick to F, G, H, K, something like this for operations. So these are operation symbols in my family. And then parameters will be P and Q, and these represent places or input types of that particular operation, and they have a given sort. Is that okay?
That's better, thanks.
Okay.
The curly braces notation you use, is it what I think it is?
Yeah, so occasionally, so this is inspired by Agda, so it means that it's a parameter which can already be inferred from the rest, and if I write too much, the notation will get really awkward. So when F is an operation of type I, I'm going to omit the first I in the notation. Otherwise, there will be way too many I's and J's running around. But I don't think that will cause too much confusion. Hopefully not.
Can the operations be recursive? And like, where is that in this definition?
Can they be recursive?
Well, like in the way that a normal container has some recursive positions.
So they can have the same input and output sort, certainly.
Oh, okay. So that's how that's being encoded.
Yeah, exactly. Okay. For now, it's just yeah, right, exactly. Okay. Okay. So every polynomial gives rise to a type of trees generated by that polynomial. So I'll just write down what that looks like as an inductive family. So this is the notation that I would use for it as a recursive definition. So a tree is one of two things. It's either a leaf, and there's going to be one leaf for every sort, or it's a node. And what do I have to do to create a leaf, to create a tree if I have a node? Well, I have to pick an operation symbol. That's the first F right here. Then I have to pick a function which assigns to every parameter a tree of the correct input type. So the way the function is written here just makes sure that every time I plug a tree into an input, it's correctly sorted. So that's why I've exposed the sort here in this parameter. So right. So if the type theory is a little bit intimidating, don't worry too much, because I'm going to draw pictures of these things, and this really is a definition of tree in the sense that that you can imagine it. Okay, so this tree, to illustrate the definition, starts with a node k, and then to each input of k, there's a function assigning the subtree which is grafted to that input. So that's all this definition says. It's a standard sort of recursive definition of trees. So I can think of the trees as operation symbols, glued together in this way. You might think of this as the syntax tree of a term. And there's a corresponding algebraic interpretation, which is the collection of trees is the collection of well-typed terms in this signature. So the collection of operations applied recursively to other operations in a way that respects the sorts, okay? So, right, so alternately, this tree right here represents the syntax of applying the operation K to the operation H, which has been applied to G, and G has two input variables of type I and J.
Before you go on, what is the type poly I? Is that the
yeah, so poly I is the type of polynomials of using the sort type I, whose sorts take values in I.
Did you write the definition on the previous slide? I may have missed it.
Yeah. Sorry. Well, yeah. So I didn't write poly I for the definition of these of this data, but that's what I mean. Okay. Right. Okay. So trees in a polynomial. If the polynomial describes a signature, the type of trees is the well-formed terms in that signature. Okay. So I'm going to need two concepts, which are fairly easy to describe. I'll just, I'm going to give their definitions, but again, if the type theory is, yeah, I apologize if it's a little bit intimidating. I wanted to be sort of precise about writing out all the definitions. You really will be able to think of this as the leaves of a tree and the type of its internal nodes, but I'll quickly run through the definition. So there's a function defined by recursion on trees, which to every tree W and every chosen sort I, or in this case J, will return the type of leaves of that tree which have sort J, okay? And how is this defined? Well, to have a leaf of a leaf, if my leaf is a leaf of sort I, and I want to know the type of leaves of sort J of that leaf, then it's just a witness, an element of the identity type that I equals J. So to have a leaf at I of type J is to have I equal J. Okay, but again, in type theory, this is a piece of data. So, and to have a leaf of a node, what do I need to do? Well, a node is not actually a leaf. So what I need to do is first pick a sort and a parameter of F of that sort. And then I need to pick a leaf of the tree attached to that sort. So phi is the function which assigns to every parameter of F the subtree grafted at that place. So to pick a leaf of this node, I just pick a direction to move in, a P, and then I ask for a leaf further down the line. Okay, so this is the definition I think you would come up with if I asked you to define the type of leaves. Similarly, there's a similar definition for the nodes of a tree. And the nodes of the tree record occurrences of a particular operation. So this will be the type of occurrences in a tree of the operation G. And how does it work? Well, what is the type of occurrences of G in a leaf? There are none, so because it's a leaf. So that's the empty type. And then how do I have, if my tree is built as a node and then some graft of a subtree, how can I have occurrence of the operation G inside this tree? Well, there's either two things that can happen. Either F is equal to G, and that counts for an occurrence of this node, or I can pick a direction to go in, a parameter of F, and I can ask for a node of an occurrence of G on that subtree. Okay, so there we go. In any case, I'm going to be using these definitions fairly informally, so your geometric intuition will work perfectly well. Are there any questions on that? Is that okay? Okay.
So you're just collecting the nodes and the leaves together into one type.
Exactly. Exactly. I want to use the type of nodes of a tree and the type of leaves of a tree. Okay. So now I'm going to introduce a new definition, which is going to sort of bring the geometry into this situation. Okay, so if I have a polynomial and I have a tree W and I have an operation F, then I'm going to say a frame from W to F is just a family of equivalences of all the leaves of W with the parameters of F. Okay, and I say a family because, well, writing it this way means that the sorts are preserved definitionally, but don't worry, you can think of it as just being an identification between all of the leaves of W and the parameters of F. So I'm about to draw a picture. It looks like this, okay? So you have a tree on one side, and you have all these lines here which are denoting a chosen equivalence between the leaves of this tree and the parameters of a particular operation F. And I've also drawn a line indicating that the root is identified with F, but that's actually taken care of by the typing. That's just because W is a type of, is a tree whose root type is I, and F is an operation whose root type is I. So, so the data that's missing to sort of identify these two things in the sense that I'm about to describe is exactly an identification of their leaves. Okay? So this is a piece of data in type theory, a particular given equivalence. And it has a sort of geometric interpretation because I'm going to interpret my tree as a geometric object by just taking its Poincare dual. And so if I do that to the above picture, I get a picture that looks like this. The tree becomes a collection of disks glued together with sort of oriented arrows. And then my operation also just becomes a disk. And so if I have an identification of the leaves of this tree with the input leaves of the parameters of this operation, and as I said, the root and the output type of this operation are identified by their type, then that corresponds to having an identification of the boundary of these two-dimensional cells. Okay? So that's the intuition behind this definition is when I have a tree and an operation, to have a frame between them is a specification of an identification between their boundaries. Okay, that's the intuition. And I'm going to use this. I'm going to use a slightly different notation. So the notation on the left here, or the diagrammatic notation here, will get very unwieldy very quickly. So so I'm going to use a kind of trick, which is I'm going to take my operation and I'm going to blow it up into a larger square, and I'm going to slide it behind the tree over here. And now the frame is actually implicit in the diagram because you see I've drawn it in such a way that the input edges of the tree and the operation are just shared. They're just identified in the diagram, okay? And so what that corresponds to is me sliding this disk on the left over in front of the disk on the right and actually identifying their boundary, okay? So, so that's the intuition. This picture here is a picture of, if you like, a two-sphere with empty boundary, where the boundary of the tree has been glued to the boundary of the operation.
Can I ask quickly how you're constructing that picture? So as I understand it, the loose ends of the top diagram correspond to nodes in the bottom diagram. Paths to the loose, between the loose nodes are edges in the bottom diagram. And then if was it the polynomial, if you have not polynomial, the operator or whatever it's called, the G's and the H's, their faces.
Right. So I'm drawing it so that the downward facing face of each operation, and that's why I've put the arrow, corresponds to its return type, and that the sequence of edges that are not the output face there correspond to its input parameters. So yeah.
Just to clarify, because Ali said something that you said yes to, but I think you didn't hear. It's the edges in the bottom diagram that correspond to the inputs and the outputs. Not the nodes.
Yeah, right, exactly. The nodes actually correspond to the space in between. So like this node here corresponds to this space, and this node here corresponds to the space in between G. Yeah, it really is. Sorry, yeah, I used the topologist language of Poincare dual. This really is kind of like a string diagram notation, if you're familiar with that. Okay. Okay, so a frame is playing the role of a boundary. Okay, so this is going to be the sort of our notion of boundary for this kind of geometry, whereas in simplicial geometry you would use a simplicial boundary. Okay, so that means that I can now ask for cells to fill this boundary. So that's going to be the motivation for the next definition. So let me say that a polynomial relation is a type family which assigns to every operation, every tree, and every frame between that operation and tree a type. Okay? So in other words, my polynomial determines a collection of boundaries, and a relation on that polynomial is a family of fillers for all of those boundaries. Okay? A choice of a type of fillers for each of those boundaries. Okay? So if I depict my, I should have tried to bend them to make this a two-sphere. I'm imagining identifying the boundaries of these two things. If I sort of make that identification then and use my diagram over here, then the relations are supposed to be filling that space, that three-dimensional space. And the notation I'm going to use in the diagrammatic notation, R will look like this. Okay, and you might notice that I've depicted R as if it was a kind of operation itself, and there's a reason for that. It is an operation in a polynomial, which I'm going to define next. Okay, so now I'm going to define a new polynomial. So far my data consists of a single polynomial P and a relation on P, meaning a family of fillers for these boundaries. And now I'm going to define a new polynomial, which is as follows. I'm going to call it the slice of P by R. And I have to tell you what its sorts are, what its operations are, and what its parameters of each operation are. So its sorts will be the operations of P. So the sum overall, so the total space of this family of operations. And so now I have to tell you what an operation of sort IF is, where F is an operation in P, because these are our new sorts. And it will be a triple of a tree, a frame, and an element of the relation. So you can think of that element R in a certain sense as determining the operation. This is the most important. And what are the parameters of such a triple? So a parameter, if I have W alpha and R, in other words, an operation, what is a parameter of this configuration of type G? It's just a node of, of sort G. I made that mistake again. It's a node of the tree an occurrence of G in the tree W. Okay, so I'm about to draw a picture of this. What do I mean by this? So let's bring back the picture that I had before. In this picture, what I'm saying is that, well, it's really the triple. It's this whole data, this whole picture, which is an operation in this slice polynomial. And but it's useful to sort of think of R, the element, the filling element, to be the sort of the most important determining factor. And I'm drawing it with inputs, and its inputs are exactly the nodes of the previous tree. That's what this definition says. And its output is this element F. Okay. So is that okay?
Can you explain what the geometric picture is for relations again?
Yeah, I'll go back. So a relation is supposed to be, if this picture shows a boundary of a two-dimensional sphere, the relations are fillers of that boundary. And it's a piece of data that you're allowed to give. So you can pick any family. Just like if I had a simplicial set and I defined the one skeleton, then I'm free to pick a collection of fillers for a collection of two simplices to fill whatever boundaries I choose to. And that's what's happening here. To give a relation is to give a choice of a collection of fillers for the boundaries determined by your polynomial. And once you give such a choice, you can define a new polynomial where those fillers become the operations. That's what I'm saying. Okay? Now, so anytime you have a polynomial, you can generate the type of its trees, right? So I said that trees were defined as soon as I had a polynomial, and I gave an inductive definition. And so what does a tree in this slice polynomial look like? Okay, it's a little bit intimidating. Well, here's an example. So I can think of it as a tree generated by my relations, but this time each of the relations carries the lower dimensional information. It carries the information of its source tree and its output operation. It carries its boundary, okay? And so that's what I've tried to describe here by drawing a particular tree. Here I'm thinking of S, T, and U as elements of my relation. And then each of them has a boundary. The boundary of S has two inputs. So you can think of these two input edges here as corresponding to the elements G and H. And similar for T, U, and V. Now things would get really horrible if I continued to use this kind of notation. So there's actually, it turns out the data determines for me that these lower dimensional informations are actually compatible with one another. So I'm going to reorganize this into a particular picture. I'm going to gather all the lower dimensional information and incorporate it into a single diagram. And when I do that, what I end up is a picture that looks like this. And so what's happening here, let me just highlight, for example, T. And if I highlight T here, what I see is its particular face information sort of nested inside of this diagram, okay? And similarly, if I highlight U, I'll see its particular lower dimensional information also embedded in this diagram. And you'll notice here that T and U share a particular face. The output type of T was the operation N, and the input type of U, U has an input of type N. And so I can sort of just think of what I've done is I've taken this picture and I've stuck it inside that occurrence of N in the picture for U. Okay? And so what
you start with a tree, and then you
Yeah.
draw rectangles around it, kind of making subtrees almost.
Right.
And then the tree you get with the data,
Yes.
each of those subtrees. Is that what you're saying, basically?
That's what I'm saying. Yes. Okay. Exactly. That that all of these subtrees are compatible with each other. If I have a tree slice, it's depicting a set of incidence relations between the lower dimensional, two-dimensional spheres. And I can draw all of the lower dimensional information in a single diagram like this.
So Matt, that diagram on the left there doesn't notate ST and U.
On the left?
No, down below on the left.
They're right here.
If you include the one on the right, so that
Yes,
them
right.
together is the notation. Okay.
Yes, exactly. So really this whole tree, this whole diagram here represents a tree in the slice. The
Okay,
tree
got it.
both the information.
Thanks.
Choosing a relation, choosing fillers, is basically choosing where you draw your boundaries around the tree.
Right, right. So I should say, actually, the first picture in the upper left is a more, in some sense, a more accurate representation of what the type theory actually says. Because if I traverse a tree in the slice, each time I encounter a node, I see its source tree and its target operation. Okay, so I'm playing some games by incorporating this, by redrawing it in this way, but I'm about to explain why that's justified. Okay, so why is that justified? For example, one thing you might notice is that each of these source trees in this picture, they're all sort of separate. I have 3 of them. But in this picture, I've drawn a much larger tree, this tree G, H, G, H, and K, as if it was a single tree. And why have I done that? Because, so starting again, so what I'm thinking of is this particular source tree. Because there's a function, which I'm going to call flatten, which extracts that particular tree, which calculates that tree from the data given in a tree in the slice, okay? So this is its type. It takes a tree in the slice polynomial of type F, of output sort F, and it calculates a tree in the previous polynomial, okay? And so this is a function which you have to write in type theory, which calculates. So that's what I mean when I say that somehow the real implementation is this sort of messy configuration, but that the interpretation I've drawn is justified because there's a function which computes this. Okay, and there's something else about this lower dimensional information, which is that I've drawn it so that the leaves of this tree actually share the inputs with the operation F. But that's not immediately obvious that that's the case. That also needs to be calculated. And that amounts to saying that when I calculate this boundary tree, that it admits a frame to the operation F. This is also something that needs to be calculated, but that you can write in type theory. And finally, a last thing that this diagram suggests that may not be obvious is that actually what is this tree that I'm calculating? It is the tree structure that is given to the leaves of this tree one level higher. So one way to think of it is a tree in the slice polynomial, its leaves carry the structure of a tree, and these functions calculate that. And the tree that I obtain, its nodes are in bijection with the leaves of the higher dimensional tree that I started with. Okay?
So all you've done so far is just basically take a tree, split it up into different parts, and then have it slice polynomial coming from that, which just describes how the different parts fit together.
Yes.
And you said you can undo that as well by flattening it.
So yeah, exactly. So let me say
this is just all trees.
Yeah, let me say it this way to give a topological analogy. Our trees our frames started as 2 spheres. a tree in the slice depicts a gluing together of two spheres, and these functions compute the boundary of that, the total boundary of that configuration, okay? So these three functions here, they're gonna come back later, so I'm recording them here for posterity. Calculate the boundary of higher dimensional configurations. They're gonna play the role, just like the frames play the role of our boundaries, so yeah, of our geometrical boundaries. These functions play the role of what you would think of in simplicial methods as the face maps. They're calculating faces, okay, or lower dimensional boundaries from higher dimensional information, okay? Right, okay, so far I've just introduced some geometry, some polynomials as a signature, and this notion of frames as a way of extracting some geometry from that signature. So now I want to add back some algebra. Okay, so polynomials are our notion of higher dimensional signature. So the way I'm gonna add relations, so the way I'm gonna make this signature interesting by imposing equations is I'm gonna try to equip P with a monadic structure. And so I don't, yeah, since I'm already running late, I don't have time to sort of explain why what I'm about to do corresponds to doing that for a polynomial, but I'll have to, you can ask me about it later. So just to start, I'm gonna make the following definition. Suppose I have a polynomial with sorts taken in I, that's not important. I'm gonna say a magma over P is a function which assigns to every tree in P returns an operation. And I'm gonna think of this, so I think of this as taking a tree, some well-typed term in the language defined by P, and spitting out, multiplying that tree down to a single operation. And because I want to be considering Cartesian monads, I'm also going to ask as part of the structure that when you give me this multiplication operation, you also specify a particular isomorphism between the leaves of the tree you started with and the operation you get by multiplying, okay? So, so this is, I call it a magma because so far there are no axioms. I've introduced an algebraic structure, but so far it has no axioms. It's just a multiplication operation. And so let me just point out that if you have a magma, then you automatically have, well, there's a sort of natural choice of relation on your polynomial, which is equality in the magma. What do I mean by that? Remember, a relation was a type of fillers for any boundary, where a boundary consisted of an operation, a tree, and a frame, so an identification of their boundary.
Can I just ask about the definition quickly? So you basically take a tree and then you take an operation and you stick it on and then you make sure the frame is correct.
Yes, it's more like the function specifies for each tree a multiplied operation. So think of it like a binary operation on a set, which is a multiplication operation, okay? So to give a magma structure is to give such a multiplication. Right, so the relation that's naturally associated to this is a filler for a particular, a configuration determined by W, F, and alpha will be an element of the identity type witnessing that the output F is the multiplication of W and that the identification alpha is the frame given by W, okay? So you take your spheres and you're going to fill them with witnesses that the output operation is the multiplication of the input. And in type theory, we have a natural choice for those witnesses. We use the identity type. Okay, so with this definition, we can sort of picture how the multiplication operation works. It starts with a tree, and then you multiply it, and you end up with an operation and a witness that that operation was the multiplication operator applied to that tree. Okay, so this is a picture when my relation is the relation given by a magma, the fillers are witnesses that F is the multiplication of its input tree. Right, so obviously this is shorthand notation. I can't also put the frame and everything in there. So this is, but I hope this illustrates the idea.
When you say multiplication, do you mean you're just taking all those letters in there and then you're sticking them?
The letters are a tree, and the definition of a magma is to have an operation which to each tree assigns a particular operation. Right.
Okay, so you're kind of like condensing it down, but it could change it.
Yeah, this is the structure that you're allowed to give. So when you define a magma, you provide me with such a function. You have to give me an instance of such a function. I'm just sort of developing a notation for talking about such a function. Okay, and so what is this function encoding? We're using this function to encode relations in our signature. So such a function, if it's the case that f is obtained by multiplying this tree, this will encode in our signature the fact that this sequence of operations is equal to the operation f. Okay, so we're using this multiplication operation to encode the relations we want our structure to have. Okay, and the fact that I'm demanding always that the multiplication operator come equipped with a particular frame, that corresponds to the fact that the number of variables on the left side and the right side are the same. So that's playing the role of the fact that this is Cartesian. In universal algebra, I think this goes, is this strongly regular? Maybe is the name that I've seen used for this when the number of variables have to be preserved. Anyway, okay. Magma is all well and good, but it's also not that great. Why is a magma not so great? Because, well, it doesn't satisfy any laws. Things could be really bad. It could return kind of silly results. And so let me explain what I mean by that. Well, so now let's suppose that we have a magma, and now let's re-examine a tree in the slice polynomial generated by it. What does it look like, and how can we interpret it? Well, what I claim is that to have a tree in the slice is to apply your relation in context, in subterms. So for example, if I had this term here, I'm waving my hands, but I have to use the mouse pointer. Sorry, I forgot about that. If I have this term here, then I could apply the operation, say, to just a piece. Like I could apply the operation just to GH. And I could have a witness that M is now the multiplication of G of H. And now I could apply the operation to, for example, a different subterm. And I could apply the operation then to the result of those two operations. So if I look at a tree in the slice, you see I can interpret it as sort of applying my multiplicative operation to subterms of the term represented by that tree. And what's bad about a magma is there's no reason for that to be consistent. So if I use my relations inside a term, they may have nothing to do with what the relation says should be the case for the whole term. So there's a kind of natural, if I stare at this picture, there's a natural question after I've multiplied it down. If I compose these relations, do I also know that this external tree, this flattened tree, this boundary, will it also be related to F by my magma? And without more structure, there's no reason for this to be the case. Okay, so this is yeah, a bad aspect of a magma. It could give completely different results when I apply the relations in context. So let's abstract that property with a particular definition. The definition will be the following. I'm going to say that and it makes sense to say this at the level of relations, but in practice, we're going to be applying this to relations derived from multiplication operators. But in general, let me say that a relation is subdivision invariant if anytime you give me a tree in the slice polynomial, so one of these subdivided trees, then the output of that tree is related to the boundary that I calculated with these two functions. Okay, so I'll draw a picture, but that's why these functions are important. Yeah, so what does that mean? Oh, okay. And yeah, so let me write subdivision invariant. I'll give a name to this predicate on relations. Okay, so but I should say that it's far from being a property. This is a structure to choose on a relation. Okay, a structure, the structure being a function which to any pasting diagram chooses an element of the relation of this form. So, shoot. Okay, well, I could have organized better here. Okay, there's a lot of notation here, but okay. So here's the observation. So suppose now that you had a polynomial and you had a relation, and suppose you give me a witness that this relation is invariant by subdivision in the sense. Then I claim that I can define a magma structure on the slice polynomial, okay? And here's its definition. Yeah, it'll be hard to write out all the types. So again, I'm going to draw a picture of it, okay? So what does this mean? So to define a magma structure on the slice, that means to every tree in the slice, of which I've depicted one right here, to give a function which will return an operation in the slice, okay? So what is an operation in the slice? It's the data of a tree, a frame, and an element of the relation. So you can see right here, given this pasting diagram, I've already shown you that this function flatten extracts a tree, that it has an associated frame. And now I wouldn't have a relation unless I demand this extra structure, okay? So, to show that it's Cartesian, you use this extra frame, but okay, let me just draw a picture. So what does that mean? I claim that these three functions that I introduced, these boundary functions, they mean that in the next dimension, there's a well-defined boundary determined by this configuration. And having this extra structure of being invariant says that there's a filler for that boundary, that I can fill it with an element of the relation. Okay. Does that make sense? Kind of? Okay. So now let me use this principle to show that if you have a magma which satisfies this property, then I claim that it's necessarily associative. That I can use this extra structure to prove that it's associative. How does that go? Okay, let's return to our example. So our example is a picture of some iterated subdivision, some sequence of operations applied to my tree. So let me just convert it to algebraic notation so that it will look more familiar, hopefully. So my first operation says that if I multiply m, n, and k, I get f. So m, n, and k give f. But on the other hand, this operation here tells me that m is the multiplication of g and h. So let me replace that in the equation. And similarly, the other one tells me that n is the multiplication of h and g. So I can depict this sequence of operations as an iterated application of multiplication. And the types just tell me that that gives me f. Now, if I have this extra invariance property, then I can multiply these relations. And I end up with the relation that multiplying this external tree also gives me f. So let me replace it here, okay? So from this extra structure, I deduce this relation that I've written right here. Now, if my relation is invariant for every such subdivision, let me just now choose a different one. So this time I'm going to choose to multiply first with h, g, and k, and then I'm going to multiply the result of that. And I get a different tree, which happens to have the same boundary as the one that I just started with. So now I have this relation that if I multiply g, h, and o, I get p. And then I have this other relation that if I multiply h, g, and k, I get o. And now, using the assumption that I have this extra invariance property, I deduce that the multiplication of the external calculated tree is p. But this tree happens to be, I mean, I've rigged it up this way, isomorphic. So I get this, but now if the right sides are equal, the left sides are equal. And so I get the associative law, okay? So actually you can be much more precise about this. You can take your polynomial and your magma and you can define what it means to be associative and unital in a very traditional sense, in a biased sense, if you like. And you'll be able to prove that if your magma is associative and unital, then its relation is invariant by subdivision in exactly the sense I just said. And there's a converse to that statement. Well, I've just shown you a part of the converse, which is that if it's invariant by subdivision, you can extract a proof that it's associative and unital. And these two maps going both ways are not an equivalence in general. I think they're a section retraction pair. I haven't completely worked this out. But I think a nice way to think of it is the analog with like a weak equivalence. What do we call it? A weak equivalence in type theory? The sort of non-coherent version of being equivalent to something versus the coherent version, okay? And so, yeah, here it's a biased version and an unbiased version, but the unbiased version is going to be a little bit better. Okay, so now I think we have all the tools we need to give the definition, okay? So let's suppose I have a polynomial and I have a magma on P. Now I'm going to define what it means for this magma to be coherent And by that I mean infinitely coherent, and I'm going to define this co-inductively. So I'm going to say that a coherent structure for M consists of, well, a proof that this magma is invariant by subdivision. Okay, so essentially in your head you can approximate that by is associative and unital. Okay, it's just a somewhat more regular way of saying is associative and unital. And then co-inductively, I showed that as soon as I have a proof that something is invariant by subdivision, then the slice of this polynomial inherits a magma structure. So I can ask co-inductively for a coherent structure on that magma, on the magma one, if you like, one dimension higher. And that will unfold to a proof that the slice magma is associative and unital. And then using that proof will give me another magma one dimension higher. And co-inductively, it will unfold to a proof that that is associative and unital. So this essentially asks for an infinite tower of multiplicative operators, each witnessing that the previous was associative and unital. Okay. Using that, a polynomial monad just consists of, well, a polynomial, a magma, and a coherent structure for that magma, and one extra condition, a proof that M is univalent, okay, in a sense that I think is compatible with what happens for categories. So I have, what, 4 minutes left? So I'm just going to run through what it means for M to be univalent, because it's actually going to give me a chance to introduce some notation and some special cases. So let me tell you what I mean by being univalent. Okay. So if I have an operation in my signature, let me say that its arity is just the sum, the total collection of all its parameters. So I've indexed the parameters by their sort. So to get all the parameters, I just sum over all the sorts. So I'll say that an operation is unary if its arity is contractible. And now I can look at the collection of unary operations. So the sum of just all the operations with a proof that it's unary. And it turns out there's an identity operation always, as soon as if I'm working in a monad. How do I get it? Well, a monad in particular consists of a magma structure, a way to multiply trees. So I can multiply the leaf, the sort of trivial tree. This gives me a canonical operation, and that operation will play the role of the identity. And now you can easily check, because everything's Cartesian, the frame will give you a proof that the identity is always unary. And so you can think of the unary operations, if I restrict to unary operations, they essentially, you can think of them as morphisms between the sorts, okay? They're operations which have a single input sort and a single output sort. So this is analogous to saying in an operad or a multi-category, I can look at the collection of unary morphisms. And now you can check that the multiplication operation restricts, because the multiplication is Cartesian, it will restrict to an operation on unary operations, which you can think of as composition. And so now you can repeat the sort of standard definition, choose your favorite definition of coherent equivalence, and say that a unary operation is an isomorphism if it has, here I've written the bi-equivalence version because it doesn't require extra coherence to state. It seems to me to be the most natural. So you can define what is what it means for an operation to be an isomorphism, a unary operation. And you can write iso M for the space of isos. And now you can check that the identity is an isomorphism. I hope this is not a surprise. It turns out to be kind of long to check this, but you can check it. And you'll say that M is univalent if the above map is an equivalence. Okay, so there's a natural notion of what it means for one of these monads or operads to be univalent. It's that restricted to the unary things, the unary equivalences look like paths in the type of sorts. Okay, so just, now that I have that notation, I can introduce a couple of special cases of this definition. So for example, let me just recall that I'll say a type is finite if it's merely equivalent to a finite set. So now, suppose I have a monad. I'm going to say that it's an infinity operad if every operation has finite arity. And I think there's a nice, there's a recent paper by Joachim Koch and Rune Houtsang and David Gepner, where they show that in an infinity topos, finitary polynomial monads and infinity operads are actually the same thing. So this definition is inspired by sort of that paper. infinity operad. In an infinity topos, this is sort of the right definition of infinity operad, or a possible definition. And similarly, I can say that I have an infinity category. An infinity category just if every operation is unary. Okay. And I can say that I have an infinity groupoid if every operation is unary and every operation is an isomorphism. And you can elaborate on this. There's more special cases that are possible. You can say a symmetric monoidal infinity category, for example, is the special case of an infinity operad where with enough universal morphisms, or where everything is representable. So if you know the definition of a multi-category being representable as being a monoidal or symmetric monoidal category, this is the definition of that. And you can say, for example, an A infinity type is an infinity category where the underlying type of sorts is connected. So you can do lots of variations on this kind of thing and extract more things, yeah, so etc. Okay, so right, so future things to follow up on. Finish the definition of algebra and therefore simplicial type. A natural conjecture, so a test for does this work? I mean, a definition is a definition, but it's only a good definition if it gets theorems. So you can very quickly imagine some theorems, and a natural theorem to conjecture is that the notion of infinity groupoid that I've described today is equivalent to type. So that would be a nice check. If you can prove something like that, that's a good indication that your definition is pretty good. And other classical theorems from topology, for example, if I look at group-like A infinity spaces, are they the same thing as loop spaces? So I hope something like this is true. There's a sort of very tantalizing connection between these kinds of monads, their initial algebras, and having a semantics for higher inductive types. It seems like a very natural way to have a kind of internal semantics for higher inductive types. So that would be a nice thing to follow up on. And of course, see if this definition is tractable. So can we repeat many of the wonderful things that are known about higher category theory starting from a definition of. So I think I'll stop here.
Okay, thank you very much, Eric. That was great. So first I will unmute everyone so we can applaud. Okay, great. And now I'll open the floor to any questions.
Does this so I'm guessing this generalizes univalent categories, because you mentioned the univalence condition, right?
Yeah.
If you don't have that, and we look, I don't know, define one categories, for example, we'll get the usual pre-category as it's known in the book.
Right.
I'm guessing.
Right.
And then there's the stack completion, which you can make it univalent after that. Is there a similar hope for a more general stack completion?
I sure hope so. Yes, I think if I think for theorems like I've suggested for A infinity spaces and loop spaces and things like this, such a theorem would be intimately connected to a construction of that sort, I would guess. So yeah, I hope there's something equivalent, but it probably it will take a little bit of time to see if we can define something like that. Yeah. Yeah, and actually I should mention there's a little bit of I added univalent as a it seems like a natural condition to add in the definition. I'm not sure if it will turn out to be the most natural thing to include that in the definition or not. Actually, I don't know. We'll have to experiment a bit more. But it certainly is there to be said, and it seems like a natural thing to do. So, yeah.
Also, a quick question. How would you define a category? Just a regular category?
So, right. So you can use this definition, and then you can just ask that the space of operations is set truncated. So that will recover the previous univalent category. So I'm actually I have a student and we're working on sort of formalizing the transition exactly between univalent categories and this notion of category. But I mean, a natural conjecture exactly is that the type of univalent categories is the type of categories in this sense with set truncated spaces of operations.
Do you mean set truncated I?
Sorry?
So what do you require to be set truncated to recover?
I think you should require the operations to be set truncated. The definition of category requires that the parameters are contractible, so that's already a very low level. The sorts play the role of the objects. So you can think of this definition as analogous to a multi-category, of sort of generalization of a multi-category, and it's the sorts that are playing the role of the objects, and the operations playing the role of the multimorphisms.
Right. So you don't expect the operations to be set truncated.
In general, absolutely not. No, definitely.
That's what you said. You meant.
Yeah, I'm saying to recover univalent category in the truncated version, you would ask exactly that.
Oh, wait, so I'm still misunderstanding that. I thought you'd want the sorts to be a set and then the operations would be a one type.
The other way around. You want the sort to be a one type and the operations to be a set.
Okay, I guess I'm confused.
Because the sorts play the role of the type of objects.
Oh, yes, of course. Okay, I was just getting it backwards. Yeah.
And univalence should imply that if the operations are a set, then the sorts are one type, right?
Exactly. Yeah, it does. The same argument, yeah.
Yeah. I have a question, another question. First, I want to say this is really awesome. I'm really excited about this.
Well,
I'm looking forward to seeing how much we can do in this way and whether it really solves the problems. It certainly seems very promising. Do you have any thoughts about, another future direction that I would want to go in is understanding the semantics. So to a real sort of proof of correctness from a semantic perspective would be to show that if you interpret this definition in the simplicial set model, say, that it gives you something equivalent to the standard notions of infinity monad or whatever that we know. Have you have any thoughts about making that connection?
So that's good. It's making that connection, it frightens me a small amount because I'm not sure I know how to do it. But maybe a really good place to start would be this recent paper by Joachim and David Gepner, where they did definition, and they do it at the level of models. So I mean, that paper was actually kind of I had put this problem aside for a while, and it was one of the reasons I started thinking about it again when they pointed out that this subtle difference between analytic functors and monads and polynomials and operads kind of goes away inside of type theory. And so
that's because you have all the automorphisms in the type of
exactly.
Right?
Exactly. It's because set level group quotients aren't effective, but they are.
Right.
Theory. So it's really nice observation, and so that might be a good place to start, I would guess.
Right. Very cool.
So on that note, I'm used to a polynomial being this sort of diagram with one leg an arrow and the other leg arrows. Does that relate to your definition here in a direct way? Are those equivalent?
My definition is just a direct type theoretic translation of that idea. It's just that in type theory, sort of whenever possible, as opposed to morphisms between types, if possible, we usually prefer to present them as families, because by presenting them as families, typically we have slightly better definitional behavior. So basically, if you take the definition as three morphisms and then try to turn everything into a family as much as you can, you'll arrive at the definition I had. Actually, there's a couple of different variations that you might arrive at. Mine is one choice of what you could arrive at.
Thanks.
Yep.
When you mean family, do you mean dependent?
Yeah, family. Yeah, I mean dependent family when I say family. Yeah.
So my understanding, the definition of simplicial type is meant to come as an instance of a definition of a sort of functor from infinity category as you've defined it into types. Could you say a bit more about the diagrams indexed by these things?
Sure, yeah. So if you think of, presumably that would be an equivalent definition. There actually turns out to be a sort of a small shortcut to getting to the notion of diagram, and that happens as follows. Well, this is meant to be a definition of a polynomial monad, which is a monoid in the category of polynomials. And the category, the definition I've given of category here, specializes to the cases where all the operations are unary. And a polynomial whose operations are unary is just a span. So the definition of category that I've given here is an internalization of the notion of category as a monoid in spans. And if you look at what a module, I guess module, is that what you say for a span, is for such a thing? It's exactly a presheaf. So I don't actually need to define the structure on the universe to say what a presheaf is. I can use this shortcut because my definition is phrased in that way to say that a presheaf is a particular instance of an algebra. And so that's the thing I have in mind. Later on, of course, a goal would be to construct the structure of a category on the universe, in which case you would hope to prove those two things are equivalent. But a nice sort of ancillary benefit of this definition is that you can get around that for the idea of a presheaf.
Have you written these down anywhere?
As I say, the definition of maybe I should go back. The definition of monad is formalized in Agda, and you can check it out on my GitHub page. As I say, the definition of algebra is slightly more involved. It requires a certain construction on monads, and so that's not quite done yet. But I don't expect there to be any real problems. Just a lot of work. So what ends up happening is there's a lot of boilerplate. You need to show that everything is stable by a bunch of pullbacks. Every time you make a construction, you have to show that it's compatible with the grafting and these three functions that I wrote, and you have to show that it induces a morphism on trees. So there's a ton of boilerplate to sort of make these definitions go through, and it's just going to sort of take some time to work through all of that.
So is time the only problem that you have with this at the moment?
As far as I can tell, I fully expect that this definition can be completed. Yeah.
Could you please give me a concrete example of the object of the EN type in your story?
Can you repeat the question?
I may repeat my question. Could you please give me a concrete example if there is an object of EN type in your story?
Okay, so not yet, not for EN type. So, well, let me put it this way. So it's not hard from the definition to define A infinity types. This turns out to be something that comes up very natural. And to define E infinity types, this is also something that that I essentially know how to construct as examples. In other words, I can construct the A infinity operad and the E infinity operad. To get the EN operads, probably the best way is to define the tensor product of two things, of two such operads. The tensor product will probably be a fairly involved construction that I haven't gotten around to tackling just yet. So with a definition of, well, the Boardman-Vogt tensor product on the notion of infinity operad, then we could define En as n times the tensor product of the associative operad. But that's probably going to take a little bit more time to get that, because that is likely to be a construction that is kind of involved that we'll have to learn how to do. So today, I can't tell you how to define the En operad. I can give you one and I can give you infinity, but I can't give you n for finite n quite yet. So.
More questions? Okay, well then let's thank Eric again. Okay, so that's it for today. As I mentioned, it's the last talk for this year, but we're continuing in January. The next talk will probably be January 24th, but please check the Hottest website to see when it is posted. And you can also subscribe for the announcements from that website as well if you'd like. All right, thanks again and see you next year.